Hello, everyone. We're going to talk about investment return today. There are different types of returns. Today, we're talking about so-called dollar-weighted yield rate. So suppose we have a cash flow. So let's draw a cash flow. And at time zero, uh, T1, T2, and then we have a capital T. And the cash flow will be C1, C2, and so forth. In the end, we have a balance at time capital T. So we do have this equation, right? If you discount everything back to time tau, actually, when we talk zero tau, it should be okay. If you back to zero, you would have a b times 1 plus I to the negative capital T that equals the summation of ck times 1 plus I to the negative T sub k and for all k. And if you wanted to set the time to be at tau, then you just multiply the whole equation by 1 plus I to the tau. Then it will be somewhere here, okay, anywhere between. The task is to find the rate I. This rate I is called yield rate. It's we by convention we call it annual yield rate or internal rate of return, sometimes dollar weight yield rate, because later on we will have a time weighted yield rates. The yield rates are a measure of how attractive a particular financial transaction may be. If you are investing, then a higher I would be better. Okay, so that's the basic theory. Let's look at a bunch of examples. What is the yield rate on a transaction in which a person makes payments of $100 immediately at time zero and $100 at the end of 2 years in exchange for a payment of $201 at the end of 1 year? For this problem, we're looking for all possible solutions. Maybe, you have a negative number, which doesn't make much sense in reality, even though occasionally it happens in the history of, well, human being, I guess. All right, so let's solve this problem. And I like to draw a timeline. It makes the problem seemingly easier to see. Okay, so time zero, 1 year, and then have 2 years. A person makes payment of $100 immediately at time zero, and $100 at the end of 2 years. And in exchange of a payment of 201, so 201 is given to the person. So let's put it on the bottom. So the top is like payment, and the bottom is like return or uh, sort of not gain, but yeah, the money that would be paid to the person. All right, so let's use the idea we discussed a little bit earlier to set up an equation. So I have 100. Right now, there's no interest. Plus 100, let's do the 2 year thing. 1 plus I to the negative 2. That equals 201 times 1 plus I to the negative 1. You can always do, well, this one is like discount back to zero. You can always do the equation at 2. So it will be something like 100 times 1 plus I squared. plus 100 equals 201 times 1 plus I first. Okay. In, in essence, they are the same. It's just have a different time. But for this problem, maybe this is a little bit easier because when I try to solve this, I'm going to multiply both sides by 1 plus I squared anyway. So either way, it's okay. We have it's a quadratic equation. Okay. 100 times, let's set 1 plus I to be x. So you have 100 times x squared minus 201x plus 100 equals 0. So it's a quadratic equation. X1, 2, possibly have two solutions. Negative b, which is 201, plus or minus the square root of b squared, so 201 squared, minus 4ac, 4 times 100 squared, then divide by 2a, 200. Okay. So you calculate it. I think the inside of the square root is actually 401, I think. So anyway, you worked it out. It is 1.005 plus or minus 0.10012. This is 1 plus I, so you subtract 1, and you would get I. Let's move somewhere here. I equals 0.005 plus or minus 0.10012. So we have two solutions. One is you add, you get 0.105, 1, 2, and so forth, which is here. Which is here. And the other one is negative, which you get 0.005 minus 0.10012, and you would get that number. Okay. Normally, if we have a quadratic equation, obviously we're able to solve. Excuse me. But if the cash flow has more than maybe say four terms, more than three terms, four or five, then you probably have a cubic function, the polynomial with degree more than two, then it's generally harder to solve. All right, so we can use the numerical method or using possibly a financial calculator. All right, so that's the first example. Let's move on to the second example. An investment fund is established at time zero with a deposit of $5,000. $6,000 is added at the end of 6 months. The fund value, including interest, is 11,500 at the end of 1 year. Find the return. The rate of return as an annual nominal rate, convertible semi-annually. Okay, so let's draw the timeline. All right. At time zero, there's a deposit of $5,000. And 6 months, another deposit of $6,000 is added. And 1 year, that's 12 months. The account has value 11500. Again, this is the balance, the other contributions. So I put them in the different positions on up and above the line or below the line. Below the line. It doesn't really matter which one is which. You can put 11500 on the top and then put 500, 5,000, 6,000 on the bottom. That doesn't really matter. Okay, so let's set up the equation. We can use annual effective rate or annual, uh, not annual, effective rate for half year because we're looking for the annual nominal rate convertible semi-annually, so 6 months a time. So the rate will be compounded twice a year. So let's just set J to be the effective rate half year. And then in the end, we'll just multiply this number by 2, we get nominal rate. Okay, nominal rate, annual nominal rate convertible semi-annually. So J is effective rate half year. So this is just one period, 6 months, right? Half year and also another period. So it's easier to deal with. Okay, let's do, probably it's easier to put everything to the time 1 year. So we have 5,000 times 1 plus j squared plus 6,000 times 1 plus j that equals 11500. And if we let 1 plus j to be x, let's simplify a little bit. 500. Uh, just get rid of 2 zeros, I guess. I don't want it to divide by 5 is okay, but let's just get rid of 2 zeros. So I have 50x squared plus 60x minus 115 equals 0. You can divide both sides by 5 further away, but yeah, let's do that. So you have 10x squared plus 12x minus 23 equals 0. So using um, the quadratic formula, negative 12 plus or minus the square root of b squared, 144 plus 4ac, so 40 times 23. Originally it's minus, right? But you have negative sign here, so it becomes positive here. And then I divide by 20 to a. Okay. I'm gonna get rid of the minus sign because you would get negative rate. So I in the common sense, we just have a positive rate. So we choose x to be the positive one. I think it's 1.03095. So our j equals 0.03095, and then you have the nominal rate compounded 2 times a year, semi-annually. So just multiply j by 2, you get 0.0619. Okay. All right. Okay. Let's move on. And the next problem is very similar. It's just we're having a different compounding scheme. So the previous information, they're all the same. It's just to find the rate of return as an annual nominal rate convertible monthly. So a monthly. So what we get J, which is 0.03095, it's the effective rate. Uh, 6 in 6 months. So half year effective rate. Half year, that's 6 months, right? So we can set this thing. J, let's J the monthly effective rate. So this is the monthly effective rate. And then you raise the power by 6. That is 1 plus J. And you can solve for J sub 12. Again, it's a monthly effective rate. And you get 0.005093. And then you multiply by 12, I get this number, which is the annual nominal rate convertible monthly. So the J12 times 12, we will get 0. I don't know, this number times 12. Well, we just look at the answer. All right, 6.11% about that. All right. Uh, that's this example. And do we have another example? Yes, we do. It's from the textbook. Oh, this is kind of an interesting problem. Jose loans Martin $12,000. Martin repays the loan by paying $5,000 at the end of 2 years and $10,000 at the end of 4 years. The money received by Jose, right, at time t equal to 2 is immediately reinvested at an annual effective interest rate of 2.4. Find Martin's rate of interest and Jose's annual yield rate. So we're looking for two annual rates. It's effective rates. Okay, two annual effective rates. The thing is that when Jose reinvest the $5,000 at the end of 2 years, he only got 2.4% interest rate. It may be different from the interest rate Martin pays. In fact, you look at the answers, actually, they are kind of bigger than 2.4. So Jose sort of lose some interest when he reinvested. Okay, so let's draw the timeline for two people. For Martin first. Okay, let's do that. For Martin, at time 0, Martin he would get, so the get will put on the bottom or the top, doesn't really matter, so put on the top just to save some space, I guess. And then 2 years, uh, Martin would pay, so put on the bottom. And in 4 years, he also pays $10,000. Okay, so that's the sort of the cash flow for Martin. And then we set up an equation, right? Let's push to time 4 years. So I have 12,000 times 1 plus I, the I for Martin, 4 years, plus 5,000, actually minus 5,000 times 1 plus I squared, because you have 2 years from this time to this time. And then I minus 10,000, and you get 0. Let's do a bit algebraic manipulation. So you let 1 plus I squared to be x, and you get rid of 3 zeros. So I have 12x squared minus 50x minus 100 equals 0. Okay. 12, 5. 3 zeros. Let me see. 3 zeros. 3 zeros. That's actually 5, and that's 10. 30, 10, 30. Yeah, okay. And then, or you can simplify further, but let's just start solving it using quadratic formula. X, you have two solutions, but I just look at it, 50. All right, let's put 1 to here. Plus or minus b squared minus 4ac, 2500. Minus becomes positive, 4ac, 48 times 0 times 10, you get 480. Um, Sorry, I think I made a mistake again. It's no 0 here. I keep saying 3 zeros cancels out, but keep adding back the 0 for 50. All right. All right, the bottom is 2 times 12, that's 24. Okay, so we're gonna choose plus because if you choose minus, you would get negative number because the square root inside the square root is greater than 25. You take a square root, the value would be greater than 5. You will get negative number if you choose minus. So let's choose the positive thing, positive sign, and we'll get x equaling 1.14467.5, something like that. And then you need to solve for I. So you take a square root of this x and minus 1. That's our I. So you do that, you would get I equaling about 7%. Okay? So I equals x, take a square root of x and minus 1. We get to about 7%. All right, so that's the Martin's yield rate. Actually, it's, I mean, the interest rate he pays. Let's talk about Jose. All right, we can still use the timeline, but change some numbers. Okay. So at time 0, Jose lends $12,000. So let's put on the bottom $12,000. And I put on the top. I don't know why, but I feel like it. And then at the end of 2 years, Jose got $5,000. Instead of putting $5,000 here and then you calculate the accumulated value at time 4, we're using different interest rate. So you really cannot put $5,000 and multiply by like 1 plus this number squared. You cannot do that. So instead, I'm going to put this number here. So $5,000 times 1 plus 0.024 squared. Okay, so that's the money Jose would get from reinvesting $5,000 into another account for 2 years. And then in the end of the in the end of the fourth year, Martin will pay Jose another $10,000. Okay, that's what the money Jose would get. So we have 12,000 times 1 plus I. This I is for Jose to the fourth equals 5,000 times 1.024 squared plus 10,000. Okay. So I think you add them up, you would get 15,242.88. And then you divide both sides by 12,000, you would get 1 plus I to the fourth. Then you take the fourth root on both sides. We would get 1.0616257. And then subtract 1, you will get this I. This is for Jose. Jose's yield rate is smaller than the Martin's interest rate is because Jose is not able to invest $5,000 into an account that has interest rate matching the original one. Okay, so he gets less, and so the yield rate will be smaller. Okay. So that's another example. There are three situations. Well, actually, three other situations. One situation, obviously, you have one root. Sometimes there's no yield rate. You in the sense that you take a square root of negative number, all right? And in the quadratic formula, you have a square root of a negative number, then you don't get any real number. So that's non-yield rate situation. Undefined yield rate, you borrow $1,000 at 4% and loan out right away at 6%. So there's a sort of arbitrage opportunity. Uh, then the interest rate is like infinity, so there's no undefined yield rate. And then sometimes there's a multiple yield rate. So if you invest $1,000 at time zero, get $2,500 at time one, and then put again, it's not invest and put it into the account $1,550 at time two. And then we'll have a multiple yield rates. But in general, in many situations, we only have one rate, and that's the case when we are focusing on. All right. Okay, so this is the yield rate. It's actually the exact real rate. The next topic is about approximating the yield rate because we are talking about dollar weight yield rate. So this section is titled Approximate Dollar Weight Yield Rate. So let's introduce some language. A is the money in the fund at time zero. It's kind of an investment, so we put on the top at time zero. And then we have a T1, T2, and so forth. Let's call the last one to be 1. Okay. T is greater than 0, less than 1. And we have C1, C2, and so forth. Okay. And in the end of time 1, we have a B in the account. Okay. You can consider A, CIs are contributions. A is the money at the beginning, and then CIs are the contribution along the way. And B is the balance at time 1. And we denote C to be the sum of all the contributions, net contributions. Sometimes CIs are negative, so C is the total, net total. And then we denote capital I to be the interest. It's an amount, it's not a rate. Okay, interest earned by the fund from 0 to 1. So interest, capital I, is B minus A minus C. C is the total of the net contribution. Okay, that's the interest earned. And let's call J the interest rate for this time period 0 to 1. All right. We use J is because is that sometimes this one period may not be annual. Could be 2 years, could be 3 years, could be less than 1 year. So that's we use J. And the annual effective rate is usually denoted by I. Okay, little I. So based on these notations, interest I can be expressed by B. Okay. What is B? B is no, hold on a second. Let's look at the cash flow. Okay, forget about B. Just look at the cash flow. So I equals the interest earned from A and the cash flow. Okay, interest earned. So this is equal to B minus A minus C. That's different story, but we wanted to use the rate to express this quantity and then come up with an equation and to solve J. That's the point. So the interest earned by capital A, which is A times J. And then for each CI, I use CI, but you use CT, it's really essentially they're the same. So you have CI times 1 plus J. Okay, I is T, for CI, the times TI. So from TI to 1, So that's 1 minus ti. Okay. And this is accumulated value, and you subtract CI, that's the interest earned from the contribution CI. Okay. And you sum up, which is this thing. Okay. I use slightly different notations here and there because uh, this notation is more concise. You don't have a TIC, so just say T 1 minus C. But the T is actually, it's an index, okay, it changes. All right. So basically, when you take the summation, you can add something like OT. That's really what it means. Okay. Um, so what's next? We wanted to approximate uh, the J. The reason is that I talked about a bit earlier that to find J, you have the power. Sometimes you don't have any quadratic equation, so it's difficult to find. So the idea to simplify the problem is commonly used in math, in financial math as well, is to approximate this quantity by linear function. Okay. You can sort of using Taylor expansion the first term, but it's really just linear approximation. So it's 1 plus 1 minus j, 1 minus t times j. Okay. So something like 1 plus x to the sum, let's use 1 plus something, I don't know, h to the power of x. That will be close to 1 plus h times x, where x is small. All right. So we're going to use this linear function to approximate this sort of power function. Yeah. Okay. Then you subtract 1, you get 1 minus t times j. So essentially, we would have 1 minus t times j. So ct times 1 minus t times j, and you take the summation. And then you have a j here, you move out, and you have a, uh, you have j equals capital I minus a, uh, actually not, I divided by a plus the sum of ct times 1 minus t. You can use ti, c, ci, that doesn't really matter, but essentially they're the same. 1 minus t. Okay. And I equals b minus a minus c. All right, so this is the approximation of the dollar weighted yield rate. Okay. Let's look at the next slide. The theory and the result are there here. J equal approximately equal to capital I, the interest earned, divided by this. So the meaning of the denominator, it's the weighted average of money invested with weights with the wait time to t equal 1. So A is invested 1 time 1, right, from 0 to 1. And CT is invested 1 minus t time unit. So it's the weighted average of the money invested with weights. Sorry, I think I said it slightly awkward in an awkward way. So it should be read as weighted average of money invested with weights time to t equal 1. Okay, so that's the correct way of saying this sentence. Okay, so um, this is one approximation. In the textbook, this is 2.6.5. And then we can further approximate it. Well, the purpose is just to make it a little bit simpler, but the approximation would be probably worse. So we approximate each t by a constant time t. So it's sort of you put all these sum up all these CIs and put into time k, right? So then you have 1 minus t, which is 1 minus k as a constant you moved out. You have a summation of ct, which is c. So we have this approximation. Further, if we approximate k by half, so basically you're sort of putting the sum of the contributions, the net sum of the contributions at time half, and then we have this formula. The goodness of this formula is that it doesn't have a c. It only has A, which is the original investment, B, which is the balance, and I is the interest earned. Okay, so let's have a look at some examples. 哎，怎么说？嗯，Why？啊，什么东西快到了？OK OK OK OK，你不要催我，你不要催我，今天是先3点都已经快到了，我下个星期二吧。啊，我知道的。 All right, let's look at this problem. On January the 1st, 1990, Martin's investment account had a balance of $10,210. He deposited $4,000 on March the 1st, 1990, withdraw $3,000 on June the 1st, 1990, and deposited $1,000 on December the 1st, 1990. At the end of 1990, Martin's balance was $12,982. Find Martin's approximate dollar weighted yield for the year using 2.6.5 and 2.6.8. 2.6.5 is the first layer of approximation, just using linear function, or it's basically the simple interest type of using simple interest to approximate compound interest. And 2.6.8 essentially puts all the contribution into half, the time half. Okay. All right. So let's draw a timeline. That's time zero, which is January the 1st, 1990. Martin has so much money in the account. And on March the 1st, so 3 March the 1st, 1990, he deposited $4,000. And on June the 1st, he withdrew $3,000. That's put on the bottom. And then on December the 1st, 1990, he deposited another $1,000. And then in the end, we have a December the 30th, 1990. So its time is 1. Okay. So we have the approximation J. Well, let's calculate I first. Yes, we need to calculate capital I. So capital I equals the balance. I forgot to put balance here. It's 12,982. So 12,982 minus the original balance, and then you subtract the contributions and also add the withdrawal. So you have 4,000 minus 4,000 plus 3,000 minus 1,000. You calculate it. It is $772. So the approximated dollar weighted yield rate is capital I, and then divided by the weighted average of the contributions. So 10,210, that is for 1 year. Okay. And then you plus 4,000. Okay, so we need to be very careful. It's actually March the 1st. March the 1st, that means 2 months passed, starting from at the beginning of the year. There are actually 10 months left from March the 1st to the end of the year. So it's actually 12 months. So it's times 12. Sorry, it's 10 months, not 12 months. 12 to 10 over 12. So 10 months over 12 months. And then for 3,000, it's actually you need to subtract minus 3,000 times from June the 1st. There are actually 7 months left, not 6 months. Okay, 7 months out of 12. And then add 1,000 times 1 out of 12. From December the 1st to the end of the year is just 1 month. Okay, so we calculated out. It's about 0.065. Okay, so that's the approximation using 2.6.5. Okay, so if we want to use further it using putting all the contributions into half, so essentially it will be something like this: 772 over 10210. That's 1 year, and then you put the summation of these contributions, which is 4,000 minus 3,000 plus 1,000, which is 2,000. So that 2,000, and you assume all the time will be in the middle, so it's half, and you calculate it out, and this number is 0.069. Of course, you can also use the formula, which is 2.6.8. The formula is, let's put it here, 2.6.8. The formula is J is approximately 2I over A plus B minus I. The reason is it's actually some algebra, not that much algebra to prove this, because originally we have I over A plus the summation of C t times 1 minus t. You add all t's, right? Now you're assuming t equals half, so you have I over A plus C times half. Okay, that's what I did here. But you can simplify it, multiply everything by bottom denominator and numerator by 2. I have 2I over 2A plus C. But C equals what? C equals, well, we have I equals, let's do a little bit calculation. So originally I equals B minus A minus C. So C equals what? C equals B minus A minus capital I. So that's our C. It's a contribution. Then replace the C by B minus A minus I. You would get 2I over 2A minus A plus B minus I, which is exactly the same. Okay, so here's like a sort of how we got that formula. All right, and then you can just plug in the numbers. Again, the goodness of 2.6.8 is that it doesn't have C. If we have C, then obviously you don't need to do that, but sometimes you don't. So 2 times 772 over A, which is 10,210, plus B, which is 12982, minus I, 772. Okay. You calculate out, it should be the same, 0.069. Okay. This problem has time 1 year. And let's have a look at the next problem, which this choice is not approximated. We are using my calculator. I won't be able to get that. You need to do something else. Okay, so I think the next problem is more complicated. On January the 1st, 1995, Jane's investment account had a balance of so much, that's capital A. She deposited $1,000 on November the 1st, 1995, and withdraw $600 on November the 1st, 1997. Her balance on July the 1st, 1998 was $9,620. What was Jane's approximate annual dollar weight yield for the 42 months period from January 1st, 1995 to July the 1st, 1998, obtained using the approximate dollar weighted yield rate. So we do need to have a sort of a 1 minus t, ct times 1 minus t. And I think it's probably easier to deal with months. So let's draw the timeline. It's a long timeline, so let's put it here. Okay. Okay, at time 0, let's just put January the 1st, 1995. This is actually 0. That's okay, it's 0 times 0. Balance A412 at time 0. She deposited $1,000 on November the 1st, 1995. So in terms of months, that is 10 actually. January 1st, it's 11. It's 10. And next one, withdraw $600 on November the 1st, 1997. Okay, so November the 1st, 1997. And the money should be on the bottom. Let's put negative sign here, okay? It's negative $600. Now, what is the time in terms of months? So from 1995, November the 1st, 1995 to November the 1st, 1997, that's about, well, that's actually 2 years. So it's 24 months and plus 10, you got 34 months. And in the end, she would have a balance July the 1st, 1998. That is 42 months. And the money she has is, the balance is what? 9,620. Okay. So the formula, J. Let's calculate I, capital I. So capital I equals 9620 minus 8412 minus 1000 plus 600. I think that's it. That equals 808. So this is capital I over A plus the summation of the contribution times 1 minus t. Oh, by the way, we are treating 42 months as one time period. Okay, so actually it's 1. Don't put like 42 here. Don't put 42 here. It's one time period. And I equals 808. And then A equals 8412. All right, let's work with the summation of the weighted average, the weighted average of the contribution. Let's work with 1000. 1000 is from month 10 to 42, so there are 32 months left. 32 over 42. All these times, when you treat the whole time period as 1, they are less than 1. Okay, that's something you need to be very careful. And now you have a minus 600. The time to the end, excuse me, is 42 minus 38, which is 8 over 42. Okay, that's it. There are no more contributions. So you calculate it out. It is 0.0891869, something like that. This is it's the J. Okay. This J is actually the rate, the effective rate for the whole 42 months. Okay, the 42 months. We're looking for the annual dollar weight yield, the annual rate. So we need to change this 42 rate to 12-month rate. Okay. So you have 1 plus I, which is annual. Okay. Uh, Let me think. Hold on a second. It's this is annual. You do this is the monthly thing. That's the monthly thing. That equals 1 plus J, and then you do the monthly thing, which is 42. Okay. So I equals 1 plus J to the 12 over 42 minus 1. Okay. This is the monthly thing. It's the 1 plus the monthly effective rate. Both are 1 plus monthly effective rate. We're just using J already, so maybe we can use 1 plus J12 means it's monthly. Okay, the monthly effective rate. All right, so we calculate out this I is 0.02471, which is about 2.47%. All right. So this is the approximation of dollar yield rate, dollar weighted yield rate. Um, um, should we continue? Let's see. The next, let's continue. Oh, there's another example. Um, okay. Should we talk about it? It takes too long. I think I'm gonna guess skip that. The answer is here. Let's talk about fund performance, which is time-weighted yield rate. Why it's called fund performance? Because sometimes when you put money in a fund, sometimes you put more money into it on the way and withdraw money on in the way. So your action may affect the performance of the fund, but this is not really the fund manager's performance. So from that point of view, we try to eliminate investors' involvement from fund performance consideration. Okay. So for example, if you're smarter than the fund manager and you put more money before the market goes up, and you take out money before the market crashes, then obviously your the dollar weighted yield rate would be bigger than if you don't do anything. But that's not the contribution of the fund manager, it's actually your contribution. And the other way around is that if you time the market badly, then the return, dollar weighted yield return would be smaller. But that should not be counted as the fund's performance, should not be counted as fund managers' performance. So we introduced this concept of time weighted yield. So this graph shows how we calculate the time weighted uh, yield rate. So suppose you have a balance at time zero, which is B0, and then the fund will grow to B sub T1. So this part is part of the fund performance. But at time T1, there's some contribution. This could be negative. If it's negative, then you're withdrawing money. If positive, then you're adding money. So at time T1, the account has this money, but this is actual money added. Okay, it could be negative, but actual money added. And then this part is not the performance part, the fund performance part. And then you're gonna the fund will increase or decrease to B sub T2 at time T2. This part it should be included in the fund performance. And then another contribution happens and so forth. Okay, so we have this graph. The time-weighted uh, return can be expressed by 1 plus J. JTW is the whole time. It's the performance of the whole time. This is annual. It's annual time-weighted rate. And this J is the uh, time-weighted return for the whole time period T. So you do the root 1 over T and subtract 1, we'll get the annual rate. And this part is calculated by the product of 1 plus JK. So what is JK? 1 plus JK is JK is the return on each time period after the contribution, after adding some money. So let's go back to the graph. Go back to the graph. This would be 1 plus J1. This will be 1 plus J2, 1 plus J3, 1 plus J, indeed the last one. Okay, so 1 plus J1 would be equal to B sub T1 over B sub T0. Okay, if BT1 is bigger, then sort of you are making money, so J1 would be positive. Okay, and then 1 plus J2 is B sub T2 over B sub T1 plus C sub T1. So this is the money you would have before the second period begins. Okay, so that's and you multiply them together. Okay, that's what the formula is about. Okay. All right, so you try to understand it, and then in terms of the example, let's look at this one. It's not that bad. All right, Jack had $20,000 in his investment account on August 15th, 1999. And then 1 year later, his balance was so much, and he deposited an additional $5,000, giving him a new balance of that. On August 15, 2001, that's like another year, Jack's account had a balance of that. Assuming that there are no other contributions to the account, find annual time weighted yield. So let's draw the graph. Okay, the graph is kind of very helpful. So at the beginning, Jack has $20,000. And then After 2 years, actually, sorry, 1 year. 1 year, okay. I said some 2 years somewhere. Sorry, it should be 1 year, 1999 to 2000. Uh, the balance is 21,200. But then she added some money. So the new balance before the next time period is 26,200. And then another year, the balance is 27,300. Okay. So 1 plus J, which is the total return, time weight return, should be equal to 21200 divided by 20,000. That's this part. And then you multiply it by 27,300 over 26,200. Okay, so that's 1 plus J sub TW. It's the 2 year time-weighted return. So to get the annual return, you basically take a square root of this quantity and minus 1. So you can just do one more step. So 1 plus I equals, the squared actually equals 1 plus J TW. This I is TW as well. Okay, this is time weighted. So I equals 1 plus J TW raised to power by half, the square root minus 1. Okay, so you do that, you would get the number is about 0.05095. If you this is 2 year, and the contribution happens in the middle of 2 years, which 1 year. So if you if you set up an equation using dollar weighted yield rate, the exact dollar weighted yield rate, you are able to solve it. That I is about 0.05. It's the exact dollar weight yield rate. Okay, but that's the problem about time weight yield rate. All right, is there anything else? I think that's about it. There's another problem. Okay, let's do that. It just has more time periods. S2 Chen notice that although the Tomorrow Fund has an excellent performance history, it performed less well when the price of gasoline experienced a sharp rise. He decides to invest in the fund, but to the extent possible, move his money away from the fund during periods when he anticipates a sharp increase in gasoline prices. On January the 1st, Chen deposits $10,000 in the fund. On March the 1st, okay, so that's two months. The fund, the balance is 102,000, and he withdrew 50,000, so 50,000, so 52,000. On May the 1st, his balance is 52,500, and he deposits 50,000, so 575. Hold on a second, 50,000. So it's 102,500. And then at the end of the year, his funds has a balance of $111,000. Find the time weight yield rate for the tomorrow fund for the year. The time yield is actually the fund's performance. It eliminates the customer's involvement. Okay, so this is actually for the funds. All right. It's just 1 year, so I think it's pretty easy to you don't need to do the conversion. So 1 plus I, it's TW, okay, time weighted, equals 102,000 over 100,000, and then you multiply by 52500 over 52,000, and then you have a 111,000 over 102,500. Okay, and you calculate it out. So ITW, it's annual, okay? It's about 0.1152. Okay, so that's the annual time-weighted a yield rate. The dollar-weighted, it's actually about what is that? 12%. It's about 12%. So astute Chen was indeed astute. All right. I think that's about it. Okay, so that's for actually the three sections. That's for today, and I'll see you the next time. Bye bye.